There we go. Something. There's things up here. Something over. Beautiful. All right. Good morning, everyone. So, quick review of what we did yesterday. So, again, we started the fact that we have an electrostatic potential energy. Same thing as minus the integral from A to B of the charge times the electric field dotted by the differential length. So again, all this means is this is my x direction, this is my y direction, this is my z direction. Forgot I got to use that z. Then A is some initial points in our three-dimensional space. B is some other point in our three-dimensional space. And then we're going to integrate along some path where dl is some differential length along here, which points in the direction at which it is that we're integrating. So this is actually what we call a path integral. Follow to that later. Okay. Okay. So at this point, it's convenient now to define a new quantity, which is what we're going to call the electrostatic potential. So notice this is not the electrostatic potential energy, but this is the electrostatic potential, bless you, where we typically are just going to call this guy the potential. So I have to be a little bit careful with my terminology. A lot of times I call potential energy just potential, but we have to be a little bit careful with that. So electrostatic potential is defined as the potential energy per unit charge. This is what we call the electrostatic potential. So this thing has units of joules per coulomb, which is what we call a volt. So notice I'm writing this V a little bit differently. I mentioned this in lab and I'm going to mention it again. So little v, I'm going to write as the velocity or the speed. V with a unibrow, this is going to be my volume. And then V with actually two eyebrows is going to be my electrostatic potential. Okay. So just so we can distinguish which one is which when we're actually talking about these things, whenever you see two lines on top, that is my potential or my electrostatic potential. Okay. So at this point in time, it's convenient to define this guy. So one thing to point out about the electrostatic potential is just like electrostatic potential energy, there's an ambiguity to this guy. So remember potential energy, especially say gravitational potential energy. When I was holding this guy up here, we said the potential energy this guy had was simply mgh, but that h is relative to some 0 points. There's no natural 0 point. I can choose that 0 point wherever I want. I can choose from the top of the computer, the desk, the floor, the first floor, etc. The value is going to change, right? Depending on where it is that that 0 point happens to be. This is the same thing because it's defined in terms of the potential energy. So this guy also has the same ambiguity, which means that we're never, ever, ever, ever going to know the absolute value of the potential. Because again, it's going to depend on where it is we take our reference point to. So all this thing says then is because of this ambiguity, we never know the actual value of the potential. But at the same time, we don't care, right? And why don't we care? So when we did conservation of energy, did we care about the actual potential energy in that case? No, what do we only care about? Like the difference, right? So what we only cared about is the fact that we looked at the change in potential energy, right? Because this was constant, or at least the same, no matter how I referred my reference points. So here we're going to do the same thing. We're going to actually look at our change in electric potential then is related to our change in potential energy by the charge. Right? So this thing is actually what we call voltage. So voltage, which is the same thing as the potential difference, is then simply the change in potential between 2 points. Right? Now, why we're mostly going to pay attention with this guy is because, as we talked about in lab, this is an easy thing for us to measure and calculate. Right? So again, in lab, we had some sort of potential region, and then we used our voltmeter here to then put one probe in one position, one probe in the other position, and then we calculated, or at least measured, and read right off what the change of potential was between these 2 points. And let's call this a, I don't know, 5 volts. Right? Now, the beautiful part about this is that what? Because potential energy is a scalar, that means voltage is also a scalar quantity, which means that it doesn't depend on direction. Right? All it is the difference between 2 points. And it doesn't matter where those 2 points are because it doesn't matter how this thing points, how I get from point A to point B. All that matters is that these guys are separated by some distance. That's it, right? So this thing is useful because what? Again, it's a scalar quantity, which means there's no direction. It's easy to measure because all I need is a voltmeter. And because of this, it is directly related to the electric field. So as long as I can measure this guy, I can then determine exactly what the electric field is because it's related to potential energy, where the potential energy is related to the electric field. Okay? So that's kind of the beautiful part of this guy. Now, what this means then is that as long as I have a change of potential, I also have a change of potential energy. So from here, we can then solve for the change of potential energy as then be equal to the charge times the change in electrostatic potential. This brings us back to conservation of energy. So now we can use conservation of energy with now electrostatic potential. So our change in kinetic energy then, plus our change of potential energy, which is going to be equal to 0 because we're going to ignore all friction terms and things like that, are now going to simply become the change in kinetic energy plus the charge times the change in electrostatic potential will then be equal to 0. So what this says then is what? If I can measure the potential difference between 2 points, I can then determine exactly what the potential energy is, and then I can apply kinetic or conservation of energy to then determine things like a velocity. Okay, so let's do a couple examples of this, and let's see how this guy works here as I open up my system. I don't want you. Examples. Oh, that's what I wanted. So potential. There we go. Plug in my stuff. So this one says that I have a parallel plate capacitor. So that parallel plate capacitor is separated by some distance of d. And inside of there, I'm going to take a charged particle between those two parallel plates, and then I'm going to shoot it from one plate to the other plate. Let me turn this guy on here. So let's look at this problem. So I have one parallel plate capacitor here. So there's this guy. I have a second parallel plate capacitor here. So here's the second guy. These guys are separated by some distance of d. And we're going to take a charged particle here of some charge of q. Okay. Then we're going to rifle this guy over. So let's put in some numbers here. I know the distance between the two is going to be 2 millimeters. And I know this plate here, let's call that V1, is going to have a potential of minus 70 volts. And then this one here is going to have a potential of V2, which is then equal to minus 50 volts. Okay. So what I know is I'm going to set this guy off with an initial velocity of 90 kilometers per second from the left plate to the right plate. And what we're told is that the particle is slowing down as it approaches this plate over here. So from that information, we want to know, is this guy a proton or an electron? And then how fast is it going by the time it gets to the second place? So let's talk about this. So in this case, again, I have my V0. My V0 is 90 kilometers per second. Okay. And we know that by the time it gets over here, its final velocity V will be less than the initial velocity. So what we want to know again is what type of particle is this? So let's look at part A first. What type of particle do I actually have? Is this going to be a positive charge or a negative charge? Meaning, is it going to be a proton or is it going to be an electron? So let's think about this. So do these overall values actually matter? Not really, right? So what I can arbitrarily do is I can set one of these equal to 0 and then make the other one a positive number. Because again, all I'm going to care about at the end of the day is from here, the change in potential. Makes it a little bit easier if I call one of these guys 0. So which one of these guys makes more sense to call 0? This one, right? So if this one is actually 0, then what's this one? 20, right? So I'm going to call this guy then 20 volts. Now, as we talked about yesterday, what side corresponds to the high potential region? So yesterday we talked about high potential energy, and we said that what? Which side of the plate, meaning is the positive charge or the negative charge, corresponds to the high potential energy? The positive side, right? So since this guy has high potential energy, that means this has to be my positive plate, and this has to then be my negative plate. Okay. Now, let's first think about this in terms of forces, and then we'll talk about it with the aspect of energy. So if this guy is positively charged, this guy's negatively charged, which way does the electric field point? This way, right? So in this case, I have my electric field in this direction. This guy is moving this way, but it's slowing down, which means what's the direction of the acceleration? This way, right? Which means what's the direction of the force? This way. So this guy's feeling a force in this direction, which means is this a positive charge or a negative charge? So if the direction of the force is in the direction of the electric field, is that a positive charge or a negative charge? Positive charge, right? So in this case, we know that Q must be positive, which means it's a proton or electron. It's a proton, right? So in this case, my charge is a proton. Okay? Now, the other way to think about this is in terms of energy. As we said yesterday, if I had a positive charge, if I drop this guy from a high potential to a low potential, it wants to go from high potential to low, right? But in this case, it's going from a low potential to a high potential and slowing down. So that's equivalent to me simply doing that. Okay. So as a given initial velocity upward, it's going to a high potential energy. It's slowing down, and it's going to turn around and come back down. Right. So in this case, because it's going from a low potential to a high potential, and it's slowing down, it has to be a positive charge. Okay. So two different ways to kind of think about it. Now, again, if this was a negative charge, what would be true about the velocity here? It'd be higher, right? So it'd be higher because again, the force would be in this direction in terms of forces, or because it's going from a low potential to a high potential, all negative charges want to go from a low potential to a high potential. Okay, so either way I want to look at it. But this guy turns out to be a proton, right? So this guy has to have a positive charge, so then it has to be a proton, which means that the charge then is going to be the fundamental charge, which is 1.602 times 10 to the minus 19 coulombs. And the mass then is going to be the mass of the proton, which is going to be 1.67 times 10 to the minus 27 kilograms. Now, in this case, again, we want to know what is the velocity by the time it gets over here. So now we know the potential difference between the two. That's simply going to be 20. We know the charge, we know the mass, so now let's use conservation of energy to determine the final velocity. Okay with this? So conservation of energy then says for part B that our change in kinetic energy plus our charge, which is the fundamental charge, times my change in potential must then be equal to 0. From here, we know this guy's going to be what? 1/2 the mass, which is the mass of the proton, times the final velocity squared minus 1/2 the mass of the proton times the initial velocity squared plus E times, again, my final potential is equal to 0. Right? Now, in this case, my change of potential is positive because my final potential is positive. My initial is 0, so I'm going to get a positive. Okay. From here, all I want to do is I want to solve for the final velocity. So let's do that. So I'm going to add this term over here, subtract this term over here. So I'm going to get a what? V initial squared minus 2 times the charge times the change of potential divided by the mass square rooted is equal to the final velocity. It's okay. Not too bad. Now, again, we can see this guy's going to be less because we have this negative sign here. So the negative sign ensures that this velocity here is less than the initial velocity. So I'm plugging my numbers. What I get in this case then is that's my final velocity will be equal to 65.29 kilometers per second. Of course, here I had to initially put this into meters per second, do all that, and then convert back into kilometers per second. That means fundamental units. So that's my final velocity. Okay. Not too bad. Let's do another one. So the next one then says, I want the third one here. Nope, that's the third one. Nope, don't want that either. There we go. So this says that we have a cathode ray tube. That's what I was playing with yesterday with cathode ray tube. Accelerates an electron through a potential difference of 5,000 volts. And then it says, what is the change in electric potential of the electron? So all this is asking is, for the first part, what is my change in potential energy? Well, we now know that the change in potential energy is simply the charge times the change in electrostatic potential. That's it. Nice and easy. So in this case, we have an electron. What's the charge of an electron? Positive or negative? Negative. So it's going to be negative E times then my change in potential. So this guy then is going to be equal to minus 1.602 times 10 to the minus 19 times 5,000. And this is going to have units of joules, which works out then to be, when I plug in my numbers, after I find it, there we go, negative 8.01 times 10 to the minus 16 joules. So next part then says, okay, so after it accelerates through the region, it's then going to come out of this region of potential difference, which is here. It's now going to be moving in this direction with now some final speed, because now there's no longer going to be an acceleration. So basically all that's happening is, again, here's my potential region. Let's call that delta V. My electron starts up inside of here, and then it's going to feel a force, so it's going to accelerate out of the region. So during this region here, it's actually accelerating, but then once it comes outside and it's outside of the potential region, it's now going to move with some final velocity, which is equal to a constant. Okay. So what I want to know then is how fast is it moving when it comes outside of the region? Okay. Again, all we're going to use is conservation of energy. So for part B, conservation of energy says the change in kinetic energy plus the change in potential energy is equal to 0. Or again, I can write this as my change in kinetic minus my charge times my change in electrostatic potential is equal to 0. Again, minus because of what we did in the previous part. Okay. So in this case, we're going to have a 1/2 mv squared minus 0, because initially this thing starts off from rest, minus E times delta V is then equal to 0. Solving this guy now for the velocity. My velocity then is going to be equal to the square root of twice the electric charge times the change of potential divided by the mass of the electron, because this guy's an electron. It's okay. Mass of the electron is, of course, 9.11 times 10 to the minus 31. Plug in my numbers. What I find in this case then is this guy works out to be 4.19 times 10 to the 7th meters per second. Was okay? Nice and easy. Conservation of energy. So again, as long as I know the potential difference between 2 points, I can use conservation of energy. Now, the beautiful part about this too is, again, do I know how my potential changes from this point to this point? So meaning as I move from one point to another point to another point to another point, do I know how my potential changes? No. Do I care? No. Right? So meaning that this thing does not have to have a constant acceleration, because again, conservation of energy is independent of a constant acceleration. So I don't care if this thing has constant acceleration or not. All I care about is the fact that it has a difference between 2 points. That's it. It's okay. So conservation. So next thing I'm going to talk about is how does now the potential relate to the electric field? So as I said a little bit ago, the beautiful part about a potential is that it's easy to measure, it's a scalar quantity, and it's related to the electric field. So let's talk about its relationship to the electric field. So first, let's talk about if we know the electric field. So let's say we know the electric field. We know this. And we want to know then what is my change of potential between 2 points? What is this guy? So we know, as we started off, the change of potential between 2 points is minus the charge times the integral of the electric field dotted by the differential length from A to B. But we also now know that the change of potential is the charge times the change in potential is then equal to minus the charge, integral from A to B of the electric field dotted by the differential length. But what happens to those two charges? They cancel, right? So what this thing finally says then is the potential difference between 2 points is related to the electric field by minus the integral of the electric field dotted by the differential length. Okay? So what does this mean? So this means if I know an electric field, I can then find the potential difference between 2 points. So for example, let's say I have a point charge. And my point charge has a total charge of Q. Then what? I know the electric field at any point here is then given by KQ over R squared in the R hat direction. Right? But now using this, I can then determine at this point, say this is my initial point, let's call that V1, and then some other point over here, V2, I can now calculate the potential difference between the two of these points, delta V. Okay? By simply taking that electric field and then integrating over it. Something we're going to do in a little bit. Okay? So all this one says is if I know the electric field, I can now find the potential difference between 2 things. Okay? Now let's do the opposite. Now let's say I know the potential, but now we want to determine the electric field. What is this guy equal to? This is the next thing we want. So mathematically, I would do the inverse mathematical operation of a path integral. I'm assuming nobody here knows what that is, so I'm going to tell you. This is what's known as a gradient. The electric field is then equal to minus the gradient of the electric potential. So this thing, by its mathematical definition, is equal to minus the partial derivative with respect to x of the potential in the I hat direction, minus the partial derivative with respect to y of my potential in the j hat direction, minus the partial derivative of the potential with respect to z in the k hat direction. I know we've kind of talked about partials before last semester, but I'll talk about it again. So a partial derivative is just a regular derivative, but you're holding everything else constant. Okay. So again, all this means is this is my x direction, this is my y direction, this is my z direction. To determine the partial derivative, say in the x direction, all I'm going to do is move solely in the x direction while holding both y and z constant. Figure out what the partial is in the y direction. I'm not going to move only in the y direction, holding x and z constant. And then same thing in the z direction, holding the other two constant. Okay. So let's do some examples of this, and let's see how this one works. Let's kind of go from there. Okay. So again, let's look at the two of these. So let's start off with the first one, and then we'll move on to the second one. So the first one here says that we want to determine the potential at a distance of r from the center of a charged conducting sphere of radius capital R with a charge of capital Q. We want to do this for different regions. So we want to know when R is bigger than capital R is equal to capital R, and then R is less than capital R. Okay, so here's my conducting sphere, charge of Q, radius of R. And we want to know what is the potential at some point R. So this then is my distance of. Okay. Now, here there's a little bit of a subtlety. So what I'm looking for here is the potential. But when I say what's the potential, what I really mean is what's the potential difference between this point and a point where it's equal to 0. Okay. So here, when we're going to find the potential at point R, what we really mean is that this is the potential difference between point R and where this guy is equal to 0. Okay. So again, because going back to our integral, this is always potential difference. So a potential at a given point is simply the potential relative to where I have 0 potential. Okay. Now, where is the only point for a charged sphere where the electric field is going to be 0? Inside, good, for a conductor. And where's the other point? What's that? Not the boundary of it, but think about the structure of the electric field. It goes as 1 over what? Infinity, right? Because it goes as 1 over r squared. So the place where the electric field goes to 0 is at infinity. And it's also 0 in this case because it's a conductor, right? But for any sphere, doesn't matter if it's conducting or non-conducting, the place where the electric field is going to be 0 is spatial infinity, okay? So what happens then in this case is way the hell out here at spatial infinity, our potential at infinity is going to be 0. So what we're going to do is we're actually going to calculate the potential difference between this point and spatial infinity. Okay, this is what this means. So anytime we talk about the potential at a given point, what we really mean is what is the potential at that point relative to where it is 0 at spatial infinity. Okay with this? Now let's go back to this integral. So this integral says that we're going to have minus the integral of a to b of then the electric field dotted by the differential length. Okay. So let's talk about this. So in this case, my r vector is going to be this one. So this is going to be my b vector here, because that's my final position. And then my initial is going to be a vector which goes all the way to spatial infinity. Okay? DL then will be along the line that connects the 2 points of these guys together. So let's say this is my path I'm going to integrate across. Okay? So my DL then is going to be this guy. Okay? Now, the other thing we know is outside of the sphere, this guy has to look like a point charge, which means my electric field then again is going to be equal to K Q over R squared, bless you, in the R hat direction. Okay? Now, let's talk about DL in this case. So DL, I'm going to use in spherical coordinates. So DL in spherical coordinates is going to be the same thing then as dr in the r hat direction plus r times d theta in the theta hat direction plus r sine of theta d phi in the phi hat direction. This is my DL in spherical coordinates. Okay? Now, before everybody panics, notice I have a dot product. So what I'm doing is I'm actually dotting this guy then with this guy. Now remember, what does the dot product do? Tells me how parallel two things are, right? So is r hat parallel to theta hat at all? No, by definition, they're perpendicular to each other. Is r hat parallel to the phi hat at all? No, again, by definition, they're perpendicular to each other, which means when I dot these guys together, the only thing I'm going to care about is the dr portion. Okay? So let's plug that in here. So this thing then, my change of potential is then going to be minus my integral from infinity to the point of R of my electric field times dr. Okay? Now, one other thing to point out here. Let's keep it this way. That's fine. Well, yeah, one other thing to point out here is that what's the direction between dr and the electric field here? So remember, at this point, my electric field is pointing radially away. So this is the direction of my electric field, but my dl is moving inward. Okay? So are they in the same direction or are they anti-parallel to each other? They're anti-parallel, which means that technically here there's an extra negative sign that comes from the dot product. Okay? What's up? Well, I'm integrating from infinity to r, right? So I'm integrating this way, not this way. Is that gonna make sense? Why not? Because my initial point is I'm starting off at infinity and then moving in to determine what is my potential at this point. So I'm taking the difference between where it is 0 and where it is at the final position. So this is my initial, so that's my initial, and this is my final, so that's my final. Is that gonna make sense? So this guy's gonna cancel with that guy and make that guy plus. Now, of course, I could do it the other way. I could start up at R and go all the way up to infinity. I could do it that way. The only thing that's gonna be different in that case then is my change of potential would now be equal to 0 minus my potential at that point. That gonna make sense? Because now my initial position is here and my final is here. Okay, so that's the only thing that's subtly different, but I get the same. Correct. Exactly. That was okay. It's always going to be a positive. Yes, correct. So what? So let's put this in. So finally, it's going to be k times q integral from infinity to r of dr over r squared. That was okay. Now, from here, what's the integral of 1 over r squared dr? Negative 1 over r, good. So let's put that in somewhere here. So I'm going to get my change of potential is then equal to minus kq 1 over r evaluated from infinity to r. Okay. One. Now, plug in my bounds. What happens when I go to infinity? Get a 0. So this thing then is going to be simply, I'm going to get a kq over r, right? Yeah, cool. So what does this mean? Then this guy then is going to be equal to my potential at r minus my potential at infinity, which is 0. So at the end of the day, what this says then is at this point, my potential at this point is simply going to be kq over r. Okay? So that's part A. So part A is basically saying, what is the potential here? So that's going to be kq over r. Next, it wants to know what is the potential specifically at r is equal to capital R. All I'm going to do is evaluate this thing at capital R. So for part B, my potential at capital R is simply going to be kq over capital R. That's it. What's that? That's a good question. I didn't mean to. Right. So that should be. There we go. So, did my bounds backwards in my head. Okay. Everybody okay? Last part is then for part C. Part C then is asking, what is the potential at any point on the inside? Well, let's talk about the point on the inside. We know that the electric field on the inside has to be 0, right? Does that mean potential on the inside has to be 0? Technically, no. So again, if we go back to the electric field, we know the electric field then is minus the gradient of the potential, which means that this is basically the same thing as the derivative of the potential in one direction. So this is going to be the same thing then as minus the derivative of potential with respect to r. Okay. Now, what this means then is what? If this thing has a potential at the boundary, which is equal to kq over r, can it then have a potential of 0 at the inside? The answer is no. All we know is that this thing says that our change of potential has to be constant, or the potential has to be constant to make the derivative here equal to 0. Okay, so all that means is anywhere on the inside has to have the same potential as what's on the boundary. Otherwise, we have a contradiction. Okay, then in that case, we would no longer have a change of potential equal to 0, which means no longer would this derivative give me 0 because it would no longer be constant. Okay with that? So all this means then is that the potential when R is less than capital R has to be the same as the potential when R is equal to capital R, because it has to be equal to a constant, which is then going to be equal to KQ over capital R. Okay? So again, even though the electric field is equal to 0, doesn't necessarily mean the potential has to be 0. It just means that it has to be constant. Okay? Here's the negative. Sorry, keep dropping my negatives. Apparently, I don't like negatives today. So. Are we doing okay? So let's do another one. So the next one then says what? So this one says it wants to determine the potential difference between two different radii, say A and B, where B is bigger than A, outside of a line charge, per which has a charge lambda, which is the charge per unit. So let's talk about this again. So now we have a line charge. So here's my line charge, which has a charge or linear charge density of lambda. Now, what I want you to do then is find the change in potential between this radius of A and then this radius of B. Okay? So yeah, what do? We know the change in potential between 2 points is minus the integral of A to B of the electric field dotted by the differential length. Okay? So in this case, I'm going to integrate from A to B in this direction. So the path I'm going to integrate along, say, is going to be this path here. So it's going to be my path of L, where my DL is going to point, say, in this direction. Now, what we know is, as we did with Gauss's law, the electric field at any point R away from the line of charge is that lambda over 2 pi epsilon naught R in the R hat direction. Okay. This was our result of Gauss's law. Okay? Now, again, if I don't remember that, I can either look it up or I can use Gauss's law to find it. Either way is fine. Now, again, if I plug this into here, even though this is now in cylindrical coordinates, again, I'm going to have a z hat, which is going to point this way, and have a theta hat, which points along this direction. But are either of them parallel to the direction of R? No. So same thing as last time, even though this is going to be complicated, the only portion I care about is the R hat direction, which means that this guy then is going to become minus the integral from A to B of my electric field, which is lambda over 2 pi epsilon R dr. Now notice in this case, I don't have an extra negative sign because now I'm integrating outward, which is the same direction that the electric field is pointing. So now I don't get a negative sign from the dot product. Okay. So cool. So all the stuff here is a constant, so it's going to give me a negative integral from A to B. Actually, let's do it this way. Lambda over 2 pi epsilon naught integral dr over R from A to B. What's the integral of 1 over R dr? Natural log. So it's going to be the same thing then as lambda over 2 pi epsilon naught natural log of R evaluated from B to A. What's that? Negative, but I brought the negative inside, which switched the order of the bounds. So I did a sleight of hand on you there. So now I'm going to be a natural log of A minus the natural log of B, but what's natural log of anything minus natural log of anything? Exactly. So this is going to get, finally, that my change of potential between the 2 points is then going to be lambda divided by 2 pi epsilon naught. And then we're going to get the natural log of A over 50. So this is my change of potential between these 2 points. Okay? What's that? This one? Yeah. Yeah, we derived that, I think, what, yesterday? When we were still doing Gauss's law, when we did the infinite line of charge, and we drew a Gaussian cylinder around this guy. We did that one. So yeah, we derived this one, I believe, yesterday. If I'm wrong about that, then that means it was done on Monday, but one of those 2 days. But I'm pretty sure it was done yesterday. It was yesterday. And again, if you didn't remember that, that's fine. You can just use Gauss's law to redetermine it, or you can look in the textbook or do something. Was that okay? Let's do another one. So this one, we're now going to do the opposites, which is knowing the potential and determining the electric field. So this wants me to determine the electric field in the XY plane at a specific points of 3 meters in the X direction, 2 meters in the Y direction, where my potential is given this way. Okay. So cool. So again, what do we know? We now know that the electric field is related to the potential by minus the gradient of the potential. Okay. Now, again, what does this mean? So we're going to have a minus partial of the potential with respect to X in the I hat direction, minus the partial of the potential with respect to Y in the J hat direction, minus the partial of potential with respect to Z in the K hat direction. So here, this is our given potential. So our potential then, V is equal to 2x squared minus 3x squared with units of volts per meter squared. Okay. So the first thing we have to do is determine the electric field anywhere in space by simply taking the partial derivative of this guy. Okay. So plugging this in, this is going to be minus the partial of 2x squared minus 3x squared with respect to x and the I hat direction, minus the partial of 2x squared minus, sorry, that's a y squared, minus 3y squared with respect to y in the j hat direction. And of course, nothing here, that's a y. Nothing here is dependent on z, so I'm going to drop that z term. Okay? Now, again, the way the partial works is anything that is not that variable that I'm taking the derivative with respect to is simply a constant. Okay? Which means when I take the partial of y with respect to x, what do I get? 0, right? So as far as this partial is concerned, this term is going to be 0 because it's a constant. As far as this derivative is concerned, x is a constant with respect to y, so this one is simply going to be 0 as well. So in this case, my electric field then be equal to what? Minus 2 times the derivative of x squared with respect to x in the I hat direction. Then I'm going to get a minus, which gives me a plus. The derivative of, so let's do it this way, 3 dy squared with respect to y in the j hat direction. Now notice I promoted now the partial derivative into full derivatives. And the reason I did that now is because this only depends on x, which means I don't have to worry about the partial anymore because the partial is the same thing as the full derivative. Same thing here, this only depends on y, so now instead of being a partial, it's a full derivative. Okay, subtle differences, but it's okay. All right, so what's the derivative of x squared with respect to x? 2x, so this is going to be the same thing as minus 4 times x in the I hat direction. What's the derivative of y squared with respect to y? 2y, so I'm going to get a plus y in the j hat direction. So this is my electric field anywhere within the plane. Okay. Now, specifically, what this wants me to do is now evaluate the electric field at the point 3, 2. So now all I'm going to do is plug in those 2 points here. So I'm going to say A then at 3, 2 is going to be the same thing then as minus 4 times 3 in the I hat direction plus 6 times 2 in the j hat direction. So anywhere I have an x, I'm just going to put in a 3. Anywhere I have a y, I'm going to put in a 2 and then call it a day. And now simply multiply. What's 4 times 3? 12. What's 2 times 6? 12. So I'm going to get a 12 in the minus 12 I hats plus 12 j hats. Or that's the same thing then as 12 times minus I plus 2. Okay. Let's do one a little more complicated. And then we'll call it a day. That was 5, right? Yeah. So this one says now it's a 3-dimensional. So my potential is given by 2x, y, z squared. And we want to know what is the electric field at the point 2, negative 2, 4. Okay. So again, we're just going to do the same thing. All we're going to do is plug in that potential into our definition of this in terms of the gradients. Right? So it's going to be the same thing as minus 2 times the partial of x, y, z squared with respect to x, the I hat direction, minus 2 times the partial of x, y, z squared with respect to y, j hat, minus 2 times the partial of x, y, z squared with respect to z, k hat direction. Okay? Now, in the first case, we're only taking the partial with respect to x, so what's true about y and z? They're constant, so they come outside of the integral or outside the derivative. So I'm going to get a 2yz squared derivative of x with respect to x. But what's the derivative of x with respect to x? 1. So my electric field then is going to be what? Minus 2yz squared in the I hat direction. Next one, again, x and z are both constants with respect to y. I'm going to pull them out. So I'm going to get a minus 2 x z squared times the partial or the derivative of the y with respect to y, which of course is 1 in the j hat direction. And I'm going to get a minus 2 times, again, x and y here are constants with respect to z. I'm going to pull them out. What's the derivative of z squared with respect to z? 2z. So this is going to be the same thing as 4xyz in the k hat direction. Okay, so this is my electric field at any point in space. Finally, all I'm going to do is I'm going to plug in my values here of 2, negative 2, and 4, which means anywhere I see an x here and here, I'm going to put in a 2. Anywhere I have a y, so here and here, I'm going to put in negative 2. And then finally, for the z, I'm going to put in a 4, 4, and 4. And then basically just multiply. That's it. So if I do that, what I finally find in this case then is that this thing works out to be 64 in the I hat direction minus 96 in the j hat direction plus 96 in the k hat direction. So this is then my okay? What's that?
Why 96 for the j hat?
Because maybe I didn't multiply right. Let's see here. So I got a 2 times 2 times. Let's see. So I got a 4 times 4 times 4 times 4, right? Right, because 2 times that is 4. So I got a 4 times 4 times 4. So that's a 4 cubed. What's 4 cubed? 64? Okay, so that should be 64. And then this is the same thing. So I have a, so that's a plus. So I have a 4 times 4 times 4, which is also 64. There we go. So they all should be 64. Yeah. Yeah, it's just me not being able to multiply numbers together as always. So it's fine. It's fine. So tomorrow, I'm going to stop here. I'm not going to do any new stuff tomorrow. So tomorrow, we're going to review, and then I'm going to give you all the group assignments that I've been ignoring since we're behind on time, as always. And then we'll pick up with all the other stuff after the exam. Okay. Yeah, it should be fine. I just have to leave here by like 11:15. That should be fine. Yeah, sounds good. Okay. Sure. Let me stop recording here.
Oh, sorry.
You're fine.